Thanks so much, Avi. Thanks, Avi. Thanks, Tony. It's really great to be here. Thanks for coming to the talk. So I'm going to talk about a project with Ryan O'Donnell and Rocco Cervidio on fooling polytopes. It's a project I'm very excited about. So I should mention that this is like a 45-minute talk. So please, let's go slowly. Please ask lots of questions.
Nothing to do with April Fool's Day, right?
No, yeah, exactly. Appropriate talk for the date. But yeah, let's try to stretch it out to 1 hour. So please ask lots of questions. But again, today will be very high level. Tomorrow I'll sort of do a chalk talk, a technical talk on one of the key lemmas in the paper. Okay, great. So we'll be talking about focusing on a very basic object, polytopes over the hypercube. These are also known as the intersections of Boolean half-spaces. So these are objects that look like this. These are functions f that can be described as the end of h1 to hm, where each hi is a half space, the sign of w dot x minus theta. So you just take the intersection, you form a polytope. Polytopes, you can view it over all sorts of spaces. In this talk, we will focus exclusively over the Boolean hypercube. So we're interested in 0, 1 valued inputs to these polytopes. As we know, these are very, very basic objects. Within optimization, they correspond exactly to 0, 1 integer programs. They show up a lot in complexity theory and learning theory. It's just a fundamental class of Boolean functions that we want to understand. And of course, it's not just over in computer science. Beyond computer science, polytopes come up in combinatorics, geometry, and so on and so forth. There are, of course, many, many questions we can ask about polytopes. We'll ask just one specific one in this talk. That was actually the next slide. But there are many complexity measures of polytopes. In this talk, we'll focus on perhaps the most natural one, which is just the number of facets. So if you view f as the intersection of half spaces, it's just the arity of your intersection. So in this case, it will be m, which I'll reserve in this whole talk to denote the number of half spaces. So there's the number of facets of your polytope, the number of half spaces. Since we're living over the Boolean hypercube, this is a number that range between 1 and 2 to the n. For this talk, we can think of m as poly n. It's perhaps the most natural setting of parameters, say n to the 10th. So we're interested in polytopes in high dimensional space, in n-dimensional space with lots of facets. N to the 10th.
Sure.
Yes?
The m is the minimal number, or is m a parameter?
M is a parameter, and we want to do as well with respect to m as possible in this talk.
I'm saying, but you might as well represent the same polytope with fewer.
Sure, yeah. So we're going to be interested in the class of m-facet polytopes. So all functions that can be described as intersectional m-facet polytopes for some m. Yeah.
And if you take vertices instead of facets, is it a completely different problem?
That's a completely different problem, I think, especially for the one that we are going to be talking about. Yeah, so, yeah.
Almost every problem.
Yeah, completely different, yeah. Yeah, so good question though. So yeah, we're going to focus on the number of facets. Okay, great. As I was saying just now, there are many questions we can ask. We'll ask one very specific and very clean question, which is that of constructing discrepancy sets for polytopes. So what's a discrepancy set? It's a special set of points, and as we'll see, the smaller the better. So this is my set of points with a very nice property with respect to polytopes. So I fixed my set of points, this one fixed set of points, with a nice property, the following property. For every m-facet polytope, f, that looks like this, at some true density with respect to the domain, the hypercube, it accepts a delta fraction of the hypercube points. I'd like to approximate this volume somehow. My special set of points is such that f accepts roughly a delta fraction of my special set of points as well. So this is a small set of points that approximates the volume of every polytope, every m-facet polytope. To additive accuracy, I've denoted as 0.01, but it's in general as a parameter epsilon. And just to emphasize, the name of the game here is de-randomization or explicit constructions. So it's not too hard to show, just because there are not too many polytopes that a random set of points works great. The name of the game here is an explicit set. Well, I'd like to give an explicit special set of points that achieves this. And I would like the size of the set to grow well with m. I'll state my results more precisely. But as many of us know, this is exactly the problem of constructing pseudorandom generators for polytopes. So let me just restate the problem in a slightly different language, but it's going to be completely equivalent. So pseudorandom generators are functions that stretch, we think of as stretching a few truly random bits to many more bits that look random somehow. And in this talk, it will be the notion will be looking random with respect to polytopes. Okay, so pseudorandom generators, epsilon pseudorandom generator, epsilon PRG for class C. In this talk, C will be the class of polytopes. It's an explicit function stretching R bits to many, many more bits. We should have in mind something like looks like this, such that the output looks the same with respect to every function in C. You wouldn't be able to tell the difference between the pseudorandom output of G versus truly uniform n bits. So in other words, the expectation of the function under the truly uniform input x is roughly the same up to epsilon as the output of this generator under a truly random seed. You can ask this question. You can think of the problem of designing pseudorandom generators for all sorts of classes. In this work, we are going to be focused on m-facet polytopes. And we'll like to minimize the seed length, which is equivalent to minimizing the size of the discrepancy set. So there are a few parameters here, n, which is a dimension, m, which, as I mentioned, is the number of facets. If you like to reduce the number of parameters, think of m as n to the 10th, and epsilon, which you can think of as 0.01, but in general, we like to keep that as a parameter that we want to optimize. And it's not too hard to see, just if we think about it for a moment, that the output of your generator, the image of your generator, forms exactly a discrepancy set. So these are just two equivalent ways of viewing out the same problem. So seed length is related by an exponential to the size of a discrepancy set. Good. One answer is it's the output of a PRG. The second answer is that it's the nice property that it's a fixed set of points in 0, 1 to the n, the smaller the better, such that it approximates the volume of every polytope. And we can see that here. This is a true volume. And this is, you can think of this as the volume under our output. You can think of this is exactly the fraction of red dots that you accept.
Do you mind if these points won't be in 0, 1 to the n? It just be like continuous? Like
Sorry?
If these points, the image of the generator, will not be Boolean.
That's a very interesting question. Yeah, that's maybe a relaxation, which could be very helpful also. But in this talk, we'll achieve actually like a Boolean output.
But you don't know whether you can achieve much.
Yeah, one thing I should say is that you can ask this same question. I had a slide, but I took out the slide, but let me say that anyway. You can ask this question also all sorts of domains, right? Polytopes live over Rn. You can endow Rn with a Gaussian measure. Somehow, like our results imply PRGs over other domains, many other domains as well, just because you can simulate, say, a Gaussian with bits, let's say. And also, like we have the same result over the solid cube, for example. So these are standard reductions that sort of, in some sense, bits are the hardest case, sort of. But you can ask this question over all sorts of domains. Sorry, yeah.
Like, what if you have a polytope which is inscribed like completely within the unit cube?
Right. Then, first of all, you have to decide what your measure is.
Yeah.
So it's a uniform measure, let's say.
Sure, yeah.
Yeah. In which case.
But then, like, no Boolean point would hit it, right?
Right. But the reduction I have in mind, it will spit out real valued points.
Oh, I see.
Right. Okay. Yeah, for sure. Yeah. Good. But in this talk, we'll focus just on the Boolean domain. But just as a remark. For two remarks. One, you can consider this question over all sorts of domains and dealt with all sorts of measures. And second is like doing it over the Boolean cube implies it for many domains and many measures. Yep.
So you define explicit as efficient.
Yep, polytime. Yeah, our generator is explicit and it's very easy to describe, as we'll see.
So this reduction depends on your construction of generator, or would any epsilon?
Good question. No, it's a black box kind of reduction. Yeah. Yeah, good question. Yeah. No, you give me a PRG over the Boolean hypercube, I'll give you a PRG over Gaussian space. Yeah. OK, so we finally have our result. It's an explicit PRG for this class of m-facet polytopes. So we give an epsilon PRG for m-facet polytopes over the hypercube with seed length polylog m, poly in 1 over epsilon multiplied by log n. The key here is a better dependence on the number of facets. So this question has been studied quite a bit. I'll go into details on the previous work in a few slides, but let me just mention that for this general question, the previous bat's seed length had a linear dependence on m. So seed length is a number that lives between 0 and n, just like how the size of the discrepancy set is a number between 0 and 2 to the n. So n is trivial here. So since the previous bat's seed length had linear dependence on m, it couldn't handle polytopes with more than n facets. Once you have an n-facet polytope, your seed length would be trivial, but now we can handle something quite a bit more than n. Right. This is non-trivial even for exponential 2 to the n to the epsilon many-faceted polytopes.
What would be a trivial lower bound?
Good. I think a random construction, which you can try to, first of all, I believe that the random construction would be optimal, is log m, so not poly, so order log m plus, not times, plus log 1 over epsilon plus log n. So there's still quite a bit of things to do here. The most glaring thing is our dependence on epsilon is not so good. We'll love to make it polylogarithmic in 1 over epsilon rather than poly in 1 over epsilon. And beyond that, I'd like to make every times into a plus.
The dependence on epsilon in the random construction is not quadratic. That's weird.
Order log 1 over epsilon. Yeah.
No, but that's a seed length. It's
Seed length, yeah.
the size of the set is the exponent.
Yeah.
I'm not used to these CLTs. Okay, thanks.
Yeah, exponentiate. Yeah, the size of the set is poly in n, m, and 1 over epsilon. Yeah.
Over epsilon squared, yeah.
Yeah. Poly. Okay, great. So, but again, I'll go into previous work in more detail. So just to say, you can take the exponential. Equivalently, we give an explicit discrepancy set of size n to the polylog m, whereas the previous best size was n to the m. So here, the benchmark, the trivial construction is 2 to the n. So we see the sort of same qualitative difference, just different by exponential. And touching on what Shai said, it would be nice to get, this is with epsilon being a constant. It would be nice to get poly n and m. So we're not there yet. Okay, great. So let me go into more detail. So this has been studied by quite a bit. The first result in this line of work is a result by Gopalan et al. Recall that a polytope is the intersection of half spaces, the and function of m many half spaces. They fool a class that is quite a bit more general, a lot more general. They fool any function of m general half spaces. You can take the majority of half spaces. You can take your favorite function of m half spaces.
You choose the function and then you let it go.
Right.
The function it fits and then.
Right. However, they achieve seed length that is linear in m rather than polylogarithmic in m.
No, the function is not fixed. It's one set that works for all functions of m hyperplanes.
So all functions
Yeah, but it's linear in m.
Right.
The seed length is linear.
Yeah. The class of
constant number of hyperplanes. Yeah,
Right.
That's a good.
Right. Yeah. It's not too hard to see that since you're dealing with such a general class, certainly any function of m half spaces is a function over m variables. Since a single variable is a half space, you cannot hope to do better than m. So that's like a lower bound. So this is a nice result. It's a broad class of functions that they fool. However, if maybe all you care about are polytopes, you can hope to do a better seed length. So in other words, can you hope to do better for the end of m general half spaces rather than any function? And indeed, this has been studied. A really nice paper, which we built a lot on, is a very nice paper with a lot of cool machinery that we leverage. It's a paper of Harsher, Clivens, and Meka, who fooled intersections of m special half spaces, so-called regular half spaces. This will be a very important notion for us. I'll define it shortly. Roughly speaking, it's a half space where no weight is too dominant. So all the weights are roughly spread out. Not all half spaces look like that. But if you give me an intersection of m regular half spaces, I should say that all the half spaces have to be regular. Then they achieve a very nice seed length of polylog m. The key here is polylog m. Let's focus on the dependence on m. And then in a recent work with Rocco, we fooled a different class of functions, so-called intersections of low-weight half spaces. Another special class of half spaces. This result is less important for this talk. I'm not going to go into too much detail, but roughly speaking, the weight of a half space is if you wrote all the weights as integers, the sum of magnitudes of the weights. So this is another sort of special class of half spaces that we were able to achieve the desired polylogarithmic in m seed length. But sort of all these results were sort of geared towards the general question of trying to fool the class of all intersections of m half spaces, which is what we do here. So in some sense, this subsumes both these results, but of course we built very heavily, as we'll see, on the machinery in this. So we remove the regularity requirement or the low weight requirement. It's not hard to see that there are many, many interesting half spaces that are not regular and they're not low weight. Okay, and we sort of achieve we'll come to this later. I'm very happy with the poly log m, very happy with the log n, not so happy with the poly 1 over epsilon. It's very interesting. They're very, very nice questions. And just to point out, even for these two classes, we'll see that we still do not have poly log 1 over epsilon. OK, great. So before diving in, let me zoom out. Yes?
Maybe you already answered this. So what's the best lower bound?
Good. It's order log m plus order log 1 over epsilon plus order log n. Yeah. So if you exponentiate, it's poly n times poly m times poly 1 over epsilon. Yeah. So there's still work to do. Yeah, of course. Great. So before diving in, let me actually zoom out. Just to mention, and I'll come back to this at the very end, this is a line of work I really like. It's sort of PRGs for geometric objects. So you can ask this question about just a single half space, right, before moving on to polytopes. You can ask, is there a discrepancy set, smaller the better, for half spaces over your favorite domain? And this has been very well studied. And by now, we have essentially optimal seed length for a single half space. And there are two possible generalizations of a single half space. We just explore one of them in this work, which is the end of many half spaces that forms a polytope. But of course, there are other generalizations as well. A very prominent one for which there's a lot of work, a lot of very nice work on, which we'll not talk about at all, is a half space is a sign of a linear form. You can think about a sign of a degree 10 form, or in general, a degree D form. And of course, you can imagine generalizations of intersections of polynomial threshold functions and so on and so forth. But I just want to point out that we are really only just chipping away at one aspect of a really nice broad line of work. Yes?
Rather sort of analogous to the threshold. Are there results that have to do with, for instance, constraints over the kinds of objects you're looking at which bound the curvature? I mean, it seems like that really the whole issue is characterizing these objects you're describing as having to sort of avoid the corners in certain ways and edges and things.
Great question. I was going to come to that at the very end. I have this dream of, I really want to understand, if you give me a class of geometric objects, what exactly is a complexity measure that dictates the seed length or that dictates the side of it. But exactly as you said, it's something like curvature or surface area or this notion of noise sensitivity that comes up a lot. So my dream result would be to give a general way of constructing PRGs from surface area or noise sensitivity. There are hints of such a connection in all these works, but we are far from proving such a generic construction. So we'll exploit heavily the fact that polytopes have small surface area. As you said, it means it's sort of big and clumsy. But I really like that question. I wish we had a more precise understanding of what dictates the seed length of, but absolutely.
It seems like it's almost becoming then an astrophysics issue, right? You should talk to the people that do information theory of whole surfaces and things like that.
I've been spending a lot of time on this line of work recently after that. And it's coming questions about exactly curvature of low degree surfaces, that they're somehow locally they look linear somehow, but we are having trouble pinning that down so far. Lots of nice questions here. Okay, great. So the structure of this talk, the first part has nothing to do with my work. I'd like to tell you about a very nice, in my opinion, beautiful connection between this problem and central limit theorems. It's a very versatile and powerful framework introduced by Meka and Zuckerman for connecting this problem we talk about, which doesn't seem, at least a priori, has nothing to do with central limit theorems, but there's a beautiful connection to central limit theorems. And we'll see, however, it's very powerful, but it sort of goes hand in hand with this notion of regularity, which I'll define. Once you do not have this notion of regularity, this framework sort of has its challenges. So the first part of the talk I'd like to tell you about this really nice connection. And the second part is our work, which is the challenges that come in going from regular half spaces to general half spaces. So there'll be some sort of decomposition theorems going on where we relate the structure of general polytopes to regular polytopes, where every facet is regular. And there are some new ideas and ingredients that's required to overcome these challenges. One of which I think is I find independently interesting. In this talk, I'm not going to have time to more than just state the result, but tomorrow I'll give like a 2-hour chalk talk on this on this result. It's sort of an anti-concentration inequality, a Littlewood-Alford theorem. You can think of it as sort of a high-dimensional analog of Littlewood-Alford. You can think of Littlewood-Alford as saying that if you have certain types of hyperplanes, you cannot have too many Boolean points that lie close to it. Our Littlewood-Alford theorem says that if you have a polytope under certain assumptions, there cannot be too many hypercube points that lie close to the surface of the polytope. So again, sort of a surface area kind of statement. Okay, but let me start with part 1, which is again nothing to do with our work, but is a very nice connection to central limit theorems. Okay, I'll illustrate this with just a one-dimensional case, that of fooling a single regular half space. And I'll see
one-dimensional case, but the one hyperplane.
One hyperplane case, right. One hyperplane, but still in Rn, yeah. Great. And yeah. So what's the connection? So forget about everything I've said so far. Let's think about central limit theorems. It says, as we all know, that the sum of many independent, not so crazy random variables, they have to be well behaved. We'll see a precise statement on the next slide. Each of them doesn't look like a Gaussian, but if you sum many of them, they start looking like a Gaussian. Independently many of them, which is an important qualification for what I'm going to talk about. If you sum many independent, say, random bits, they start to look like a Gaussian. There are many notions of what looks like means or what convergence mean. And in this talk, we'll focus exclusively on CDF distance, also known as Kolmogorov distance, which is, as we all know, for any threshold, the weight that you put under that threshold is roughly the same as that of a Gaussian, or in other words, the height of this triangle. As we'll see, this notion of convergence syncs up perfectly with half spaces. Right, so when are you accepted by half space is when your linear form falls below a threshold. So we'll see that this is sort of the right notion to be working with when you're thinking about linear threshold functions. But of course, there are convergence in other metrics as well. Okay, so here's a well-known central limit theorem. It's explicit. It gives like quantitative bounds. So we finally see this definition of regularity. An epsilon regular linear form, we're going to take the sign of it soon, but just a linear form is epsilon regular if no weight is too dominant. If every weight is at most an epsilon fraction of your 2 norm. So sort of the canonical regular linear form is when all the wi's are 1, which is the majority function. And indeed, in the majority function, no weight is too dominant. Sort of the influence is well spread out.
Epsilon has nothing to do with the epsilon you mentioned.
No, yeah, sorry about that. Yeah, so there's nothing to do with that. Or at least let's not think about it as anything to do with that for now. Okay, great. If you give me such a linear form, then we're in business. It says that S under uniform random bits, if you sum many of them, it starts to look like a Gaussian. And that epsilon is exactly how close you are in CDF distance to a normal. Okay, and just one quick remark, sort of this notion of regularity is crucial. And we'll see, I'll emphasize this again. So as a sort of a silly but kind of an important example, consider suppose X1 is super dominant. Right? So given the same way how majority is the most regular half space, in that all the wi's are the same, this is the most unregular half space. Just W1 is 1 and everything else is 0. And it's not hard to see that, of course, a random bit, this just says that a random bit looks nothing like a Gaussian. So sort of the regularity, and if you have seen proofs of the central limit theorem, it really shows up in the proof. The fact that no weight is too dominant helps you converge to a Gaussian. But at least for this part of the talk, just assume that we're dealing with regular half spaces. Okay, so what does this have to do with the problem that I started the talk with? This is just a classic theorem in probability. So, but I claim that's very, very natural. The connection is very, very natural. So hopefully this slide will make that obvious, or hopefully clear. So a central limit theorem, so fix a regular linear form. For concreteness, just think about it as majority. We're interested in the behavior of this linear form under uniform random inputs. X. So the CLT says the following, that S of X converges to a Gaussian in CDF distance. Meaning, by the definition of CDF distance, for every threshold theta, the probability that S of X lengths below theta is roughly the same as the probability, the mass that a Gaussian places below theta. That's exactly what it means for S of x to look like a Gaussian. So what does it mean to fool the regular half space? S of x, sine of S of x minus theta. It says that, well, the probability that your half space is yes under uniform random inputs is roughly the same as the probability that your half space is yes, says yes under pseudo-random inputs, which is that under uniform x, S of x below theta is roughly the same as pseudo-random y, S of y below theta. So once we have this, then sort of, at least just by pattern matching, the left-hand sides are identical. It's just the right-hand side, and on one hand, you want to compare it, you get to compare it with a Gaussian. On the other hand, what you really want to compare it with is a pseudo-random input y. So given this, it's sort of suggests the use of, well, first of all, the triangle inequality. Second of all, it would be very nice if there's some sort of pseudo-random version of the Berry-Essen theorem. If, for example, if this CLT allowed the left-hand side to be pseudo-random, then I'm good, right? Because I can apply the regular CLT, and I have my pseudo-random CLT, and using the Gaussian as the middle person, I get this by the triangle inequality. And that's exactly the proof strategy that Meka and Zuckerman employed. Hopefully a picture makes it clear. So good. So here's what Meka-Zuckerman did. They observed that the Berry-Essen central limit theorem says S of x, again, S is a regular uniform, looks like a Gaussian. It's in CDF distance. They de-randomized the Berry-Essen theorem. Now, rather than x, the bits being independent and uniform, they cooked up a clever pseudo-random random variable y, such that S of y still converges to a Gaussian, just as if S of x, just as if you fed S uniform random bits. So they proved this de-randomization of a central limit theorem. And as a nice bonus, they get to apply the triangle inequality and say that, forget about the Gaussian, S of x and S of y are CDF close. And once you have done that, you have done nothing more and nothing less than fooled the sine of S of x. In fact, you have fooled the sine of S of x minus theta for every theta. OK, so that's the game plan. So let me say one more, spend one more slide on the PRG. The parameters are perhaps not super important, but it's sort of the structure of the PRG is what we are going to use a lot. So your job is to using as few random bits as possible, assign values to n bits. So the first thing you're going to do is hash the n variables into 1 over epsilon squared buckets. So there are many, many variables in each bucket. And then you're going to assign values within each bucket according to a constant-wise independent distribution. And then you're going to do it independently across buckets. So within a bucket, you're not doing it independently, but across buckets, you're doing it independently. So they're sort of like being very careful about the amount of randomness they're going to use for the central limit theorem to go through. Indeed, they show that, given this very randomness efficient way of assigning values to variables, this Berry-Essen central limit theorem cannot tell the difference. If you fed a regular linear form, this distribution, it still converges to a Gaussian.
So the same proof applies under this assumption, under this Meka assumption?
Right. So this, you can think of it as a strengthening of the Berry-Essen theorem, if you like, showing that it continues. No, I wouldn't say so. Yeah, it's very clever. It's sort of reducing it to, yeah, here's the proof. It's a reduction to Berry-Essen, just a classic Berry-Essen, over 1 over epsilon squared many variables. So think of each bucket as a mega variable. And indeed, right. And indeed, I'm doing things independently, which is what Berry-Essen requires.
So what do you use the fact that within each bucket
constant-wise independent.
Right. The moments, the small moments are fine. That's all you need. That's why limited independence.
Yeah. If you look at the proof of, and it will come up, well, unfortunately, I don't get to do details, but sort of at least like a proof of it goes via Taylor expansions and things like that, and you do like a constant, you do a Taylor expansion up to a constant, truncated as a constant, and that's exactly the constant you need for the amount of independence. In fact, it's like 4-wise independence will suffice. Yeah. But it's sort of a very nice reduction, sort of to Berry-Essen, but Berry-Essen over 1 over epsilon squared, many mega variables. And exactly as Avi said, like these central limit theorems, they hold not just over Boolean inputs, but over all sorts of, yeah. Yeah, and if you're well spread out to start with, and then you hash into buckets, like the buckets are also well spread out, which is why you get to apply Berry-Essen. Okay.
And these two epsilons are the same?
Every epsilon is the same on this. Exactly. So you start with an epsilon regular half space. Yeah, all the epsilons are the same. Right. Good. Good. And it's not hard to see that the seed length, there are 1 over epsilon squared in many buckets. Each one is constant-wise independent. The seed length is very nice. It's log n over epsilon squared.
But this could be log 1 over epsilon.
Yeah, but it's right, for sure. And indeed, for a single half space, you can achieve log 1 over epsilon. Yeah, I should say that the paper of Meka-Zuckerman does this is just merely a warm up for them. There's a lot of other very nice things in there. In particular, achieving log 1 over epsilon for a single half space. Yeah. Good. So great. And in this talk, think of all PRGs as simply this very nice simple generator. Hash into buckets. Every bucket constant-wise independent. Well, not constant-wise in our case. Our thing will be depending on M, but having this general structure, which is certainly explicit. And it's not just explicit, it's very simple.
And the hashing is pairwise independent?
Good. No, constant-wise independent. I'm not sure pairwise independent suffices. Yeah, you need it to be well spread out. But yeah, constant-wise independent. OK, great. So that's a very nice connection showing how sort of connecting this problem of pseudorandom generators, discrepancy sets to central limit theorems. And next, I want to spend one quick slide on the generalization of it to not just a single half space, but intersection of many, but still under the assumption of regularity half spaces. It's the same overall framework because it's so nice and versatile, but there are you need many new cool ideas and ingredients that Harsha, Clivens, and Meka execute in this work. So let's do that. OK, so at the very core of this result I just described is the classic Berry-Essen central limit theorem, which says if you sum many real value random variables, none of them are too dominant, you converge to a Gaussian. And sort of if you had to guess, the central limit theorem that underlies Harsha, Clivens, and Meka is a high dimensional analog of it. You're not summing just a single real value random variable, but Rn value random variables. And you sum many of them, they prove a multidimensional central limit theorem. Multidimensional central limit theorems have been very, very well studied before that paper, but they needed a specific version that they had to prove themselves, that you converge to a multidimensional Gaussian now in multidimensional CDF distance. Okay, so first of all, they prove something that has nothing to do with pseudorandomness. They prove just a very nice, independently interesting central limit theorem.
And in this central limit theorem, the dependence of M on M is already bad.
No, the dependence on M is good.
It's good.
Yeah,
and the randomized one. Yeah.
Exactly. But under the assumption of regularity, it's good. And this is why previous CLTs, they were able to handle better convergence, or better notions of convergence, but they didn't have such a good dependence on M. So here, the convergence had a very good dependence on M, which is crucial. But it's very specialized as it had to be to CDF distance, which CDF distance, as we'll see, corresponds to the end of half spaces, sort of. But we'll draw that connection soon.
So you didn't say yet what is the multidimensional CDF, right? Or you did?
CDF distance. No, but I can say it in one sentence, and I'll say it again later. It's every orthant, translated orthant, you place the same amount of mass.
It's just axis parallel hyperplanes, basically.
Right, exactly. Which corresponds to the intersection of half space. It's just like single-dimensional CLT, single-dimensional CDF distance matches up perfectly with a single half space. Multi-dimensional CDF distance syncs up perfectly with the end of half spaces because.
Yeah, you put the threshold in every dimension.
No, yeah, exactly. Yeah, not off, right.
Oh, okay.
Yeah.
Yes.
Yeah, these are orthants in Rm space, not Rn space. Yeah. Good. Great. So, but anyway, so this is the setup. They're not dealing with a single regular half space anymore. You have a matrix think of every row as the weights of a regular half space. So every row, the weights cannot be, they have to be well spread out. If A is such a special matrix, they prove using their own central limit theorem that AX converges in CDF distance to a multidimensional Gaussian. They didn't just do this, they de-randomized the central limit theorem, proving that the same thing also holds under pseudorandom Y. And now they throw away the Gaussian and they say, oh, AX and AY are CDF close. And if you think about it for a second, this is exactly what it means to fool the intersection of half spaces described by the matrix A. And in fact, with respect to all threshold vectors theta, not just a single threshold vector theta. So very nice. And what's the PRG, you may ask? It's the same thing. Hash into buckets and do limited independence across buckets, independently across buckets though. So they looked at a proof and they were like, this is all we need. This is just the amount of independence we need for the proof to go through. Great, we can finally get to our work. It's more than enough time, so please continue to ask questions. On the intersections of, so these are very nice, but hopefully what's clear is that the notion of regularity is essential for all of them. Because like the core machinery is a central limit theorem, where even forgetting about, intersections of half spaces, just a single non-regular half space, the central limit theorem breaks down and you have no middle person to go to. So good, just to say what I said all over again, the main challenge in trying to go from like a single half, like regular half spaces to non-regular half spaces is this regularity assumption. Just forget about M half spaces, a single half space, such a convergence is false in the dominant WIs. Recall this silly example of just W1 being very dominant. You see that the weights are not spread out, you don't look like a Gaussian.
For a general half space, prior to this, did we even know how to estimate the probability given a linear form?
Good, so I'm cutting out some background work. You may think, oh, like the result I'm describing is about intersections of M general half spaces. What about a single general half space? Indeed, we have PRGs for a single general half space as well.
So no, I just meant in the white box, can you estimate the volume of the polytope if you're given the facets?
No, yeah, so even for approximate counting, like, yeah, the previous best thing was just to do it via PRGs, which meant that you ran in time n to the m. But now, given our PRG, you can do it in time n to the polylog m, right? But even for white box, yeah. It'd be very interesting to do better for white box, yeah. Okay, so this work we have to bypass, not because we're trying to be clever or trying to save on seed lengths, just by necessity. So here's an equivalent statement of our result. Maybe it doesn't mention half space at all. Let A be your favorite n by n matrix. The weights do not have to be spread out at all. The first row can be 1, 0, 0, 0, 0, 0, 0. So you think of every row as encoding the weights of a general half space, not necessarily regular. As we saw, even for m equals 1, AX is not going to be close to a Gaussian, so it's certainly not going to be close for the matrix form. And if it's not close under uniform, it's certainly not going to be close under pseudorandom. However, the problem of fooling a polytope is exactly the problem of showing that AX and AY are CDF close, or exactly the problem of cooking up a Y so that AX and AY are CDF close. So this is exactly our result. We prove that there is a pseudorandom Y such that AX and AY are CDF close.
So not Eigen inequality.
No.
Yeah, why not? I mean, it can be a different distribution than that.
Right, yeah, but not the Gaussian for sure. Yeah, by necessity. Yeah. Good, so that's our result. Nothing to do with half spaces, although it's sort of just an equivalent statement. Okay, but somewhat surprisingly, or maybe not so surprisingly, we still employ CLT proof techniques, but sort of in a regime where a CLT provably doesn't hold. So just to say a little bit more about that, we go via this so-called Lindenberg replacement method, which is for theoretical computer scientists, this is just a hybrid method. We'll go through it in the next slide. It's a very powerful technique for proving central limit theorems, but also in pseudorandomness, in cryptography. And it's the strategy for the all regular case, where you replace things one by one and show that sort of a half space or polytope cannot tell the difference. And then you do a union bound. But of course, our setting of non-regularity, we need new ideas and new ingredients. There are two new ingredients. One is sort of something comes into play which maybe one may not expect. The PRGs for CNF formulas, which is a very, very well studied class since the work of Avi of functions. It's a special case of polytopes if you think about it, because CNF is an N of ors, and every or is a very special kind of half space. And it comes into play. The fact that we have very good PRGs for CNF formulas is helpful for us. And as I said, tomorrow we also have a new sort of Littlewood-Alford theorem for polytopes, which I'll go on tomorrow. I will give the chalk talk tomorrow about. OK, so in my remaining time, I'd like to tell you what I can about the proof of this. OK, so this is a structure of our proof. First of all, I'll touch on a useful decomposition of polytopes, sort of relating this notion of a regular half space with general half spaces, sort of a regularity lemma. Next, we'll talk about a smooth version of the problem. For that, I have to tell you why the current version of the problem is not smooth. Tell you the smooth version. The main work comes in proving the smooth version. So this will be the technical portion. And this is going from the smooth version to the actual version is where the Littlewood-Alford theorem comes in. So I'll end my talk just by stating the Littlewood-Alford theorem. And tomorrow I'll actually prove it, the Littlewood-Alford and deconcentration inequality. OK, so let's start with this decomposition theorem. So a regular half space is one where no weight is too dominant. So for me, when I visualize a regular half space, I think of a picture like this, sort of every weight, no weight is too, there are no spikes. However, the weights of a general half space can be spiky. Xn minus 1 can have huge weight. So here, this is just a single half space. A very useful lemma in this context is a lemma of Rocco, showing that every half space like this can be made regular by restricting only a very small set of variables. It's not 100% true. If you think about it, there are half spaces that cannot be made regular no matter how many variables you restrict. But there, after you restrict a few variables, it becomes very close to constant. For the purpose of this talk, ignore this asterisk and just pretend that every half space can be made regular by fixing a few variables. And the proof is sort of, in hindsight, not difficult. This is not regular. Well, if you had to kill off one variable, which would you choose? Kill this one off. Is it regular? Not yet. Not yet, but now it's regular, sort of a potential function. Well,
and the notion of regularity changes after fixing. So you think of this as a decision tree or like an adaptive or non-adaptive?
For a single half space, they do not change. The notion of regularity doesn't depend on the threshold.
So it will always be the same value.
Exactly. It's like a junta.
Yeah.
Like you fix. Yeah.
Anyway, would you care about it, or if it's a constant, then?
Right. That's fine, yeah. But just to sort of, just as a remark, it's been regularity lemmas for low degree polynomials have been studied. That there, things changes because weights collapse on each other and they interact in very interesting ways. But for half space, something that's nice and convenient is that when you kill this one off, none of the other weights changes. False for degree 2 polynomial, for example. OK. Great. So here's the regularity lemma as a picture. You give me any half space, your favorite one. The first thing I'm going to do is sort it by magnitude. It's not hard to see. Well, the regularity lemma says that if you want an epsilon regular tail, then you only have to kill off roughly 1 over epsilon squared many what we call hit variables, and you become regular. OK. In this talk, think of this parameter as like a constant, like say poly log n. So you can kill off poly log n many variables and get to something that's regular. So if you want something concrete to have in mind, don't think of it as constant, think of it as poly log n. OK, so how do you apply the regularity lemma? You have it for a single half space. You can, of course, apply it for, you apply it individually for every half space in your polytope. And indeed, for any specific half space you look at, you can just kill off poly log n many variables, and you get like an epsilon, you get like something that's regular that remains. So we'll love it if it's just a green picture. But it's this like purple spikes that's messing us up. So just to remark, each head is small, but sort of the heads can be different for all half spaces. and there are m many of them. And again, think of m as larger than n. And this is like sort of like the bottleneck in previous arguments, why they required m to be less than n. But if m is greater than n, say n squared n to the 10th, you could cover all the variables. The spikes could cover all n. So sort of a very natural strategy is like, I really wish the purple spikes was not there. Let me kill all of them off. Well, if you're dealing with greater than n many half spaces, you have killed off all the variables. Right? So roughly speaking, this like naive strategy of just trying to kill off all the spikes is not going to work. It could work if the number of half spaces is less than n, which is why previously you could, and indeed this comes into play. Right? If you're dealing with root n many half spaces, which is still very interesting, you just kill off all the heads. OK, great. So there's a useful mental picture to have in mind. Every row is an adversarial A. There are no assumptions about it. But in my mind, I'm going to mark every row with a few spikes. I'm going to think of it as spikes. And then my goal is to show that this matrix A, my goal is to cook up a pseudorandom Y such that AX and AY are close in multidimensional CDF distance. And no surprises here, our Y is just a Meka-Zuckerman generator, but with different parameters. Okay, think of the number of spikes in each row as polylog m. Yeah, that's probably a good regime to think about. Okay. Great, so let me talk about this is a very standard technique for, in this line of work, a smooth version of the problem with that out of the way. So our goal is to prove, I have to first tell you why the current version is not smooth. So our goal is to prove that AX and AY are CDF close. What does that mean? Following up on conversation, my answer to Shai's question, it shows that for every vector B in Rm, AX less than B is roughly the same as AY less than B. So sort of geometrically, any orthant rooted at B, the mass that AX places in here is roughly the same as the mass that AY places in this orthant. Let me just rewrite things a little bit. As I write O sub B as the 0, 1 indicator of this orthant, you're just trying to find the probability that you fall in the orthant. Just expectation of AX versus AY. The reason why this is not a smooth version is because it's a discontinuous function. Right? This is 1 here, it falls off this cliff, and it goes to 0 outside the orthant. Right? It would be very nice, it would be very convenient if this was a continuous function. So the smooth version that we'll work with it's sort of like a smoothed out version of this orthant. This now not a 0, 1 valued function, but it maps to the range 0, 1, which I'm going to call O tilde. So the first thing I'm going to do is first fool this O tilde, the smooth approximator, and then I'll show how to go from the smooth version to the actual version, which is where maybe intuitively anti-concentration type things come in, trying to say that the smooth version is a good proxy for the hard version. Okay.
This idea of smoothing comes in previous PhDs for this. Yeah.
Absolutely. Yeah. I should say that this is certainly not our ideas, and not even without in central limit theorems, for example, this is how they prove central limit theorems. You prove closeness with respect to some modified version of your test function, and then you use anti-concentration to go from the modified version to, in fact, a lot of CLTs just deal with like Lipschitz test functions, which are just smooth by definition. Great. So let me just spend a slide on it. It's sort of a very standard way of smoothing out a function. You add some Gaussian noise to it. So O tilde of V is just expectation of O, which is a hard function, of V plus some lambda amount of Gaussian noise. So there are two, so this comes out in work in central limit theorems. There are two important properties of O tilde. Roughly speaking, we want it to look like O. Right? So it should be a good approximator of O. So what that means is that there's a small sort of shell around the orthant where you go from 1 to 0. But inside this orthant, you should be very close to 1. And outside it, you should be very close to 0. And you go smoothly from 1 to 0 in this small error region. The smaller, the better, because the smaller it is, the better the approximator. But here's where the tension comes in. You want this to be a good modifier in that it goes very nice and smoothly from 1 to 0. You have small derivatives. This is a technical condition. It sort of says that for any point, if you sum all its cth order partial derivatives, think of C as a constant, like 4. then the sum of magnitudes of the partial derivatives is this expression. The one thing I want to point out is that this grows polylogarithmically, which is very nice for us and very nice for previous work as well. So you're summing m to the c many things, and yet you're bound on the absolute magnitude of the derivatives is polylog in the dimension. So this is really extremely helpful and crucial for us. So if there's one thing sort of like I like to point out is this nice modifier, and it's not hard. It's a problem about Gaussians. You can calculate it, but it's a very nice fact about Gaussians that this sum of derivatives is polylog m, and this feeds directly into the fact that our seed length is polylog m.
So lambda we should also think of as a polylog m.
Yes. Yep. 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 So, and just to point out, there's a tension between 1 and 2, right? How the smaller the rate region is, the better the approximator is. But of course, the smaller the rate region is, my derivatives are getting larger and larger and larger. So I have to choose lambda appropriately, and lambda, as Avi said, is exactly going to be polylog m. Great. So, okay, now is the most technical part of the talk. Let me go slowly. But it's not going to be too long. It's a few slides, and we'll end the talk. The last one is just one slide. Okay, and sort of so far, it's a lot of previous work. I think this is really where this, in fact, yeah, item 2 is sort of very standard in even central limit theorem proofs, and this useful decomposition of polytopes is Rocco's work from a while ago. So yeah, this is where the work comes in. So let me go slowly. It's not going to take too long. Okay, my goal is to fool, not O, my actual goal is to fool the orthant, but we're going to fool O tilde. In your mind, think of O tilde as like something that looks like O, basically. Not so important. The fact that we can take derivatives is important, but maybe in your mind, just imagine O tilde as like an orthant. Okay, and our goal is to, it's exactly to show that, you know, under X being uniform, sorry, my goal is to show that AX is close to AY, where AY is this Meka-Zuckerman generator. So I can certainly view uniform axis as this way, where, you know, I hash in the buckets, but every bucket, rather than uniform, rather than R-wise independent, is uniform. This is certainly also a uniform distribution. But describing a uniform distribution in this weird way, the proof sort of suggests itself, which is I'm going to swap out one bucket of uniform bits for a bucket of R-wise independent bits, bucket by bucket, and show that a modifier cannot tell the difference. And then union bound over all swaps. Okay, so this is a standard technique, sort of in Meka-Zuckerman and Harsha-Cliven's Meka. You start with all buckets being uniform, start with the left picture, swap out a bucket of uniform for a bucket of orange R-wise independent bits, bound the error, and then I'm just going to union bound across all stages. Okay, so what I'm going to do in the next few slides is I'm going to describe how we're going to bound the error incurred by swapping out one bucket of uniform bits for one bucket of R-wise independent bits. And of course, the larger the bucket is, the better my seed length. So I'm going to swap out a big bucket for a big bucket. Okay, so I'm going to try to show that the orthant modifier cannot tell the difference when I swap out one big bucket. Meaning,
so just before the
yes.
previous one, so because we were doing it one by one, because you insisted that buckets are independent, you might as well think you have just one bucket. Absolutely, yeah. So what these arguments do not exploit, yeah, so sort of for any fixing of, I'm not using the randomness of the other bucket. Yeah, exactly. Which is, it feels like that can be leveraged somehow, but I do not know how. So basically, I think in a lot of hybrid arguments, just fix any outcome of the other buckets. I'm going to swap out one bucket. I'm not going to use the randomness of the other buckets.
Will the bound and the small error come from the partial derivative bound?
Yeah, that feeds in, and also, yeah, for sure. Yeah.
But it's not it. It's not just that.
No, it's not just that. Yeah, there are many moving parts to this argument. Yeah, but that's certainly, one of the components that come in.
Also fix the partition of the variable.
Good. The randomness of the partition comes in the fact that the weights are well spread out. So no, I do use that randomness. Yeah.
So you think about the number of buckets as the number of variables with lot of influence?
Good. It sort of syncs up that way. Yeah. I'm not going to be able to get any knowledge out of that. I'm not going to be able to say that, oh, but it is true. The number of buckets is the number of large variables. So I'm not going to say that, be able to say with high probability, only one large influence variable falls in every bucket. I'm going to be able to say something like this. In expectation, a constant number, or maybe even a sub-constant number, falls in each bucket, but we don't see how to leverage that. Yeah, good question though. Yeah.
But any improvement on the value of epsilon in your bound or any bound will have to get rid of this independence of bound.
For sure, yeah. Even in the one half-space case, yeah, they're very interesting bottlenecks. Roughly speaking, like a central limit theorem, you don't get exponential convergence, right? The error of a central limit theorem is 1 over root n. And then 1 over root n is exactly the same. It's exactly why we get 1 over epsilon squared in like the PRG. So they're very interesting questions here. Okay, great. Good. So I'm going to focus my matrix A was actually over all n variables. I'm going to shrink it down to just that bucket here. And there could be a spike in there. I'm going to show that when I swap out this bucket, it's roughly the same under uniform versus constant-wise independent. So the first thing is just notation. I've restricted my attention down to the buckets, but as we see, there could still be spikes or hit variables in here. So I'm going to write it just as just h plus t, where h is all the hit variables, and t is like the green part. So it's, as the color coding suggests, h is the spikes and t is the well spread out tail. Just notation. And of course, what I'm trying to show is that hx plus tx is close with respect to the orthant modifier as a test function versus hy plus ty. And just as a side note, this is where we start to depart from central limit theorems and de-randomization of central limit theorems. The underlying assumption, just by assumption of central limit theorems, is that you have no spikes. So this H matrix is what's new and the challenge that we have to deal with. And in the rest of my time, I'm going to focus on this presence of H. In other words, you can think of previous settings as H being empty matrix.
Yeah, so you can forget about T, right?
Yeah, exactly. So previous work will help us handle T, although we have to open up the proof somehow, not in a black box fashion.
You have to open up the proof because this is, plus,
yeah, exactly. Yeah, but the same ideas come in. Yeah. Great. But I'll focus on the H part, which is the special part in our argument. So, okay, here's what we want to show. You have two matrices, H plus T, and you want to fool it with respect to the orthant modifier. But we have nice properties of H and T. T is like the CLT people's their favorite setup. All the entries are spread out, they're small. So that's nice. H, not so nice, but also H has a nice property, which is every row is sparse. Right, so you have every row is sparse plus some spread out thing, and you want to fool it. So both matrices have nice properties that we can exploit. So you're trying to show that Y fools this function, Z mapping to HZ plus TZ under the test function O tilde. So writing as a plus, it's maybe suggests, and you think of T as small. So you suggest bounding the error, and this again standard using Taylor expansion. It's not so important, the exact expression, but there's a 0th order term, there's some intermediate terms, and then you truncate it somewhere and you get an error resulting from the Taylor expansion. Let me just point out one thing, is that what's special in our setup is that even the 0th order term is not clear that that you can fool the 0th order term. But now that's a very nice question because it really highlights the fact that H is present in our argument. So I'm going to spend one slide on that. This same step in previous proofs is like a no-op because H, this is like a constant, but now it's not a constant in our setup. So I'm going to prove that there's a way to fool the 0th order term of the multidimensional Taylor expansion. And just a remark, the way you fool it is you fool every term of the Taylor expansion. And think of C as a constant. So certainly you have to fool the 0th order term, which is a very nice, clean question. Can you design a pseudorandom Y so that a sparse matrix when hit by uniform versus a sparse matrix when hit by the pseudorandom, the probability that you fall in the orthant is roughly the same. And maybe if you are a computer scientist, this starts to sound sort of familiar and you're in good shape. But let me go through that. Okay. Sorry, I'm running a little over. Can I have 5 minutes? Yeah. Okay, great. Good. So I'm trying to say that Z maps to O tilde of HZ, where H is every row of H is sparse. When do you, okay, again, think of O tilde as O. When do you fall in an orthant? Well, when your first coordinate is less than something, and your second coordinate is less than something, and your third coordinate is less than something. And every row is sparse. So it's sort of like the end of M things, M conditions. Each condition is like a sparse condition. So it's like the end of Hunter's, end of, but let's go through that. So O tilde is just the average of O under some Gaussian noise, which actually is not important in this setting. Just for any fixed outcome of this averaging, when do you fall in an orthant? You fall in an orthant when M things happen, all happen. So you take the product of M conditions. Well, your first row when hit by Y should fall under B1. Your second row when hit by Y should fall under B2, and so on and so forth. And every row of H is sparse. So every condition is like a threshold function, but it's over a few variables. So
we can assume these few variables got independent values.
Exactly, right. Right, but you're taking the end of it. Yeah, which is why, yeah.
They are correlated.
Right.
Inequalities are correlated,
yeah.
But each inequality.
Yeah, I have enough, I can afford to make it so that every condition is exactly like a CNF case. Yeah. So this is the end of, let me click. This is a product end of K Hunters, where think of K as polylog of N or polylog of M, which is not too hard to show. It's a with K CNF, and it's a very, very well studied. How to fool to design a Y such that this is true is very standard, and we have lots of generators with fantastic C length for this condition. So this is that sort of clear? This is like one of our main ideas of how we deal with the fact that we have this like H, which denotes like the spiky things that we do not like. But we get rid of it using the fact that the end of M spiky things is a CNF somehow. And we can fool CNFs extremely well. So we can show that in fact all these spikes don't really bother us too much. Okay, so just to wrap up, what we did is we considered a multidimensional Taylor expansion. We're in the middle of like swapping out one bucket, right? We take the Taylor expansion. I showed how to fool like the 0th order function, 0th order term in the Taylor expansion. We have to fool all the intermediate ones. It's more complicated because now there's this like T thing, but it's the same idea. We also leverage the product structure of an orthant, meaning an orthant is an N, the sparsity of H, and use the fact that we have very good generators for fooling CNF formulas. And finally, we have to deal with the error term. And here we use the fact that this nice fact gifted to us by Benkers, also leveraged by Harsha, Klivans, and Meka, it's not surprising that a Taylor expansion involves like some sort of derivative condition. We use this very nice fact that the sum of absolute values of M to the C many derivatives is at most polylog M. Yeah. Okay, so what we just showed is how to bound, at a very high level, how to bound the error incurred in one swap. We do this for every bucket, and we take a union bound.
Sorry, what was C?
C is the order of your Taylor expansion.
What are you going to set that to?
4. Yeah, it's a
Function of the pairwise dependence.
within each bucket, right? Yeah, it's sort of, yeah, it's an absolute constant. Yeah, we're not taking it to be polylog M. Yeah. Okay, so we're just going to union bound with all swaps. Let me just one last slide to say, to lead up to what I'm going to talk about tomorrow, which is what we have showed is how to fool like the orthant modifier, right? Sort of a proxy for the orthant where you're allowed to go sort of like smoothly from 1 to 0. Oh, just to emphasize, the reason why we need to work with the modifier is we're doing a Taylor expansion, right? We need to take derivatives and things like this. We cannot take a sort of the derivative of like a discontinuous function. And we have fooled this, and we want to show that we can fool this. At a very high level, when will we be in trouble? We'll be in trouble if AX or AY puts too much mass in this red strip. Right, and if you're able to bound the mass that AX places here, it's not too hard to show that, now you can go from this to this. And that's exactly what I'll prove tomorrow, sort of a Littlewood-Alford theorem showing that AX doesn't put too much mass in the orthant boundaries. Which this is, yeah.
Yeah, so this is just to say what you said, that this is an anti-concentration bound, and it's a surface area bound. Exactly,
yeah. There are lots of hints as to connections to surface areas, but yeah, we are having trouble proving a black box theorem. So anyway, this is in Rm. In Rn, you think of your m-facet polytope in Rn, it's just the amount of mass you get by expanding your polytope a little bit, how many Boolean points you catch. And tomorrow I'll prove that you do not catch too many Boolean points. Sort of polylog m-ish kind of bound. Okay, let me wrap up. Yeah, anyway, tomorrow. Okay, great. Good. So our main result is that we give a PRG for high-dimensional polytopes with many facets, with C length as poly log m, poly in 1 over epsilon times log n. The previous best had a linear dependence on m, although we built very heavily on previous ideas and work. Let me state two future directions, one very high level and one very concrete. The very concrete question is this, maybe a somewhat technical question. I would love to get a better dependence on epsilon. It's mentioned sort of this is still open even for regular half spaces, even for low weight half spaces. So getting these this log 1 over epsilon comes to very, very interesting questions about CLTs, getting exponential convergence. Again, having to bypass the Gaussian by necessity.
M equal to 1 also?
M equals to 1, there are some nice machinery you can do to get log 1 over epsilon, which falls apart for m being large. M being constant, there's some machinery you can do to get log 1 over epsilon. Yeah. So that's a concrete question. A high-level question, sort of as I said at the start of the talk, it'd be very nice to, I think this line of work I really like about PRGs for geometric sets, and what exactly is the complexity measure at play here, right? It's intuitively, it's how wiggly you are as a set, which is just, which is things like surface area or noise sensitivity, as we like to call them, things like this. It'd be very nice to prove a black box theorem saying you give me a class of objects with a noise sensitivity bound or a surface area bound. Here's my PRG with C length that grows with the surface area. But we are very far from, well, I don't know. Yeah, it'd be nice to prove such a theorem. Yeah. All right, thank you very much. Sorry for going over time.